The first one, work measurement. Most definition. Most way of working. Fourth, most systems and sequences. The fifth, standard time, relation between most, normal and standard time, and certification. As explained in the work measurement module, the time for the best method is calculated using one of the following work measurement techniques: work sampling, time study, most. The outcome of a work measurement is the normal time. At Jabil, we use 3 ways to calculate the normal time. Depending on the situation, we decide what technique is best to use. When the work measurement is for non-repetitive irregular activities, we could apply work sampling. When the work measurement is for repetitive work, mostly for value-add direct labor, we better use time study or most. If the product is not in production yet, or when the best method is not defined yet, we can apply most. If the product is in production and the process follows the best method, we can apply time study. Each work measurement technique has its own advantages and disadvantages. At Jabil, some typical areas where most can be applied are quoting, high volume assembly, continuous improvement. PMTS, or a predetermined motion time system, is a work measurement technique whereby times established for basic human motion are used to build up the time for a job at a defined level of performance. It is a collection of basic motion times, technique for obtaining a standard time by analyzing and subdividing a task into elemental motions, assigning preset standard times for motions and summing these to obtain a standard time for the whole task. Popular predetermined motion time systems are Methods Time Measurement, MTM, Work Factor, Predetermined Time Standard Systems, Myers, Most. When we look at the work content, we can split each job in different tasks. Each task consists out of different work elements, most level. And each work element is a combination of different basic motions, MTM level. Most, or the Maynard operation sequencing technique, is a predetermined motion time system that is used to set the standard time for a worker to perform a task. It is designed to simplify and speed up the process of setting engineered time standards, and is the primary work measurement tool used to establish standards here at Jabil. It is not only calculating the time, but also make the engineer think to make sure this is done for the best method. To calculate these standards, Most uses a catalog of standard times assigned to the fundamental motions that are often repeated that make up an activity, assigns time values, or time measurement units, TMUs, associated with these motions to each step in the process, and then adds them together to derive a time standard for the task at hand. Most times represent ranges of motion, and since these times are represented by a range of values, precise measurements are not required. However, incredibly accurate results are still produced with this technique. Without explaining all the details yet, here are some examples of most calculations. While using most, we should always follow a similar method. Identify the object, describe the method, construct the sequence model, and finally, calculate the corresponding TMU. There are several most methods with different levels of detail. Basic most, mini most, maxi most. At Jabil, basic most and sometimes mini most is the one we used most often. Each of these has their own area of application and corresponding detail and speed of usage. How you benefit from most. Most is the fastest way to accurately measure work and to evaluate method improvements. Most is simple to learn and easy to apply, while retaining the accuracy of more detailed work measurement systems. Most eliminates the need for a stopwatch to time and subjectively performance rate the associate. Most generates consistent results. Most focuses the analyst's attention on analyzing the method instead of just the time. There is no need to time workers with a stopwatch because a most data card predetermines index values for each defined work method. Therefore, also no performance rating is needed. By focusing on the working method rather than on performing rating the worker, most can contribute to a more efficient workplace by identifying method improvement opportunities. Most is based on the movement of objects, all of which move in one of two ways: freely through space when picked up, while maintaining contact with another surface or along a controlled path. When developing most, extensive analysis of work measurement data indicated that certain sequences of movement consistently repeat. These sequences form the basis of most and are organized into the following fixed sequence models: general move, controlled move, tool use, equipment use. General move is the manual movement of an object from one location to another freely through space. Examples include stocking a can on a grocery shelf, putting a washer onto a bolt, placing a label on a box, and dropping a part into a bin. The general move sequence model used to identify this movement consists of a fixed series of letters called parameters that represent various subactivities. Each sequence model in most is further broken down into phases to help guide the applicator through analysis. The parameters and phases are as shown here. The order of the sequence model defines the events or actions that take place in the work method. Workplace conditions and the defined work method determine the variation of each parameter. A for action distance, for example, which is assigned an index value 0, 1, 3, 6, 10, etc., taken from a most data card. To convert the formula to time, the index values are added together and multiplied by 10 to get the time measurement units, TMU. For example, an associate bends to get a heavy case from the bottom bay of a racking system, and then walks 3 steps to put the case on a pallet. This is shown in most as A1, B6, G3, A6, B0, P1, A0. 1 plus 6 plus 3 plus 6 plus 1 plus 0 equals 17. 17 times 10 equals 170 TMU, or 6.12 seconds. Controlled move describes the manual displacement of an object over a controlled path. In other words, either movement of the object is restricted in at least one direction by contact with or attachment to another object, or the nature of the work demands that the object be deliberately moved along a specific or controlled path. Examples include pushing a grocery cart, flipping a switch, sliding a box on a conveyor, opening and closing a toolbox or copier lid, and pulling a lever to actuate a machine. The controlled move sequence model is similar to general move, but with 3 different parameters. For example, after placing a check in a register drawer, a clerk reaches to contact the drawer and pushes it back into the register by seating it in place. This is shown in most as A1, B0, G1, M3, X0, I0, A0. 1 plus 1 plus 3 equals 5. 5 times 10 equals 50 TMU, or 1.80 seconds. The tool use sequence model covers the use of hand tools for such activities as fastening or loosening, cutting, cleaning, measuring and writing, as well as certain additional activities requiring mental processes, such as reading and inspecting. Examples include cutting open a box with a knife, fastening a nut with a wrench, reading 3 words from a purchase order, and wiping a surface with a cloth. The tool use sequence model uses all of the parameters from the general move sequence model, as well as one of 7 new parameters used to identify the tool action. For example, an operator grasps a small ratchet 6 steps away, walks back to the work area, and loosens a nut with 8 wrist turns. The ratchet is laid aside within reach. This is shown in MOST as A10, B0, G1, A10, B0, P3, L16, A1, B0, P1, A0. 10 plus 1 plus 10 plus 3 plus 16 plus 1 plus 1 equals 42. 42 times 10 equals 420 TMU, or 15.12 seconds. The equipment use sequence model contains values for such administrative activities as using a keyboard and keypad, stapling, stamping, and filing. Examples include stapling 2 receipts together, filing a report in a filing cabinet, clicking a computer mouse, stamping the date on a check, and totaling numbers on a keypad or adding machine. Equipment use follows the same sequence model format as tool use, but with 3 different parameters, and was developed for administrative work in any industry. For example, an associate walks 5 steps to a computer terminal and enters her 4-digit personal identification number to access a software system. This is shown in MOST as A0, B0, G0, A10, B0, P1, K3, A0, B0, P0, A0. 10 plus 1 plus 3 equals 14. 14 times 10 equals 140 TMU, or 5.04 seconds. MOST can be applied to any type of work for which a method can be defined and described, and may be used to determine labor requirements, define and control labor costs, set goals, plan and schedule work, and establish a baseline for continuous improvement. The time required by a qualified worker working at a pace that is ordinarily used by workers when capably supervised to complete a task by following a prescribed method and without interruptions. The result of a MOST analysis is a normal time. Adding allowances to the normal time constitutes a time standard. Normal time equals manual time plus process time. The normal time is the basic work content of a job or process, which can be defined as the sum of manual time, hand, and process time, machine. An allowance, or PF&D, is given to take care of personal needs, P, fatigue or rest time, F, and minor delays, D. Normally, this is mentioned as percent of the basic work content or the normal time. But in case of man-machine environment, there is no fatigue percent applied for the automated process. Please check the man-machine training module for more details. This allowance is necessary to get the standard time which a normal operator can achieve on regular basis under normal operational conditions. So the standard time is the normal time plus PF&D allowances. The way to define the correct PF&D percent will be explained in a separate training module. As part of our enduring quest for quality and accuracy, only certified